Have you heard about sodium-potassium pump, which helps to maintain the cell potential? How will you measure the concentration of sodium and potassium ions in and out the cell? The Nernst equation will help you to measure the concentration of ions and determine the membrane potential. In this class, we will learn about the Nernst equation. You might have learned that when the concentration of all the species involved in a half cell is unity, then the measured electrode potential is known as standard electrode potential. The cell potential is concentration dependent. Then, how will you measure the cell potential if concentration is not known? It was Walter Nernst who developed an equation so that it allows to calculate the cell potential at non-standard conditions. He gave the equation E cell is equal to E0 cell minus RT by NF ln Q, where E cell is the cell potential at non-standard conditions. E0 cell gives cell potential at standard conditions. R is the universal gas constant, that is 8.314 joules per Kelvin mole, and F is the Faraday's constant, 96487 coulombs per mole. T is the temperature in Kelvin, and N is the number of electrons involved in the process, and Q is the reaction quotient. For a particular reaction, as shown here, the reaction quotient is given by ratio of products of molar concentration of products to that of reactants raised to their stoichiometric power. Substituting for Q, you can rewrite equation number 1 as E cell is equal to E0 cell minus RT by NF ln C raised to C D raised to D divided by A raised to A B raised to B. Note that concentration of solid is taken as unity. By converting natural log to the log to the base 10 and substituting the values of R, F and considering T as 298 Kelvin, the equation reduced it to the following one, that is E cell equal to E0 cell minus 0.0592 divided by N log C raised to C D raised to D divided by A raised to A B raised to B. Next, we will see the relation between standard reduction potential and equilibrium constant. Consider Daniell cell with zinc anode and copper cathode, as you can see here. The half cell reactions at anode and cathode are as follows. At cathode, Cu2 plus will combine with 2 electrons to give copper, and at anode, zinc gives to zinc 2 plus and 2 electrons. Then the overall reaction will be zinc solid plus copper in aqueous medium giving copper solid and zinc 2 plus in aqueous medium. If the cell potential for half cells is represented like this, from the equation for overall reaction, cell potential of Daniell cell would be written as E cell will be given by equation number 2 minus 1, that is E cell will be equal to E Cu2 plus bar Cu minus E zinc 2 plus bar zinc. Expanding and simplifying, you may infer that the E cell depends on the concentration of both copper and zinc ion, and the final expression would be E cell will be equal to E0 cell minus RT by NF ln zinc 2 plus divided by Cu2 plus. As Daniell cell starts functioning, the concentration of zinc ions keeps on increasing while that of copper ions keeps on decreasing. At the voltmeter, at the same time, the voltage of the cell as read on the voltmeter also keeps on decreasing. After some time, you may see the voltmeter reads 0 and the concentration of copper and zinc ions remains unchanged. At this stage, we can say that the reaction has reached equilibrium. Therefore, equation 3 can be represented as follows, that is E cell will be equal to E0 cell minus 0.059 divided by N log zinc 2 plus divided by copper 2 plus will change into E0 cell equal to 0.059 divided by N log zinc 2 plus divided by copper 2 plus. As you can see here, since E cell is 0. For Daniell cell, the equilibrium constant Kc is given by the ratio of concentration of zinc ions to that of copper ions. Substituting this information in equation number 4, we will get equation number 5, that is E0 cell equal to 0.059 divided by 2 log Kc. By rearranging this equation, we will get log Kc equal to 2 E0 cell divided by 0.059. In general, we may write log Kc is equal to N E0 cell divided by 0.0591. Thus, equation 7 gives the relationship between equilibrium constant of a reaction and standard potential of the cell in which that reaction takes place. That is, E0 cell equal to 2.303 RT divided by NF log Kc. It may be understood that for those reactions where equilibrium constants are difficult to measure, they can be calculated from their corresponding E0 value. Next, we will look into the relationship between Gibbs free energy and cell potential. The electrical work done per second can be obtained from the product of electric potential and total charge passed. If EMF of the cell is E0 cell and NF is the total amount of charge passed, then the work done can be written as E cell into NF. As the reversible work done by a galvanic cell is given by the decrease in its Gibbs energy, you may write and delta Rg0 is equal to minus NF E0 cell. Here, delta Rg0 is the standard Gibbs free energy, E0 cell is the standard cell potential, F is the Faraday's constant, and N is the number of electrons involved in the process. By equating with the expression for E0 cell and equilibrium constant, you can come to the conclusion that delta Rg0 will be equal to minus RT ln K. So, now I hope you are familiar with the relation between Gibbs free energy and equilibrium constant. With these equations, you will be able to calculate equilibrium constant and Gibbs free energy for an electrochemical cell. With this, I hope you are clear with Nernst equation and various relationships between equilibrium constant, Gibbs free energy and cell potential. Now, can you tell me the variation of cell potential with variation in concentration of ions? With this, I will summarize this video.
Manorama Horizon. Learning made simple.